In the first two problems, we have two blocks that are on top of each other. One is attached to a rope and the other is on an incline. And we're asked how many forces act on block A and on block B. To solve this, we'll need to draw free body diagrams. For block A, there's a force due to gravity, a tension force from the rope, a normal force from being in contact with block B, and the dots on B represent friction, and so there will also be a frictional force acting on block A. To determine the direction of that, we need to think of what would happen if the force wasn't there. Block A would slide down the incline, so therefore the friction force points up the incline. So block A has 4 forces acting on it. Repeating the same process for block B, we have a force due to gravity, a normal force from being in contact with the ground, a normal force from being in contact with block A, and a force due to friction that is opposite in direction but equal in magnitude to the force due to friction acting on block A. So counting those all up, we have 1, 2, 3, 4 forces on B as well. In the next problem, we have a force given as a vector acting on a 5 kilogram object that moves from distance dI to a final position of dF. Force is in newtons, position is in meters, and we're asked what is the work done by the force. To calculate work, we need to compute the dot product between force and displacement. So the first step is going to be calculating the displacement based on the final and initial positions of the object. To do that, we need to subtract these two vectors, and so dF is 2i hat minus 3j hat. From that, we need to subtract dI, which is a 2i hat plus 1j hat. Subtracting like components, 2 minus 2 gives us 0i hat, minus 3 minus 1 gives us a minus 4j hat, and now we can compute our dot product. So our force is 3i plus 10j dot our displacement of negative 4j. Computing our dot product, we have 3 times 0 for our I contribution, plus 10 times minus 4 for the j. This one's a 0, and so we're left with negative 40 joules of work done. In the next problem, a block of mass m is pulled horizontally along a floor by an applied force T as shown, and we're asked about the vertical component of the force exerted on the block by the floor, i.e. the normal force. Drawing our free body diagram for this, we have a force due to gravity, normal force, and then the tension force at some angle theta to the right. We're asked about the vertical component of the force, meaning the normal force on the block, and so to solve that we need to write Newton's second law in the y direction. So we add up all of the forces in the y direction, and that will be all of our up forces, normal, and the y component of tension, minus the force due to gravity. And since the block is moving horizontally, that means it has no motion in the vertical direction, so all of these forces need to add up to 0. Solving for Fn, we see that it's equal to mg minus t sine theta, which is answer choice A.